Okay, so here we are asked to find an expression for the expectation of z squared, and we have z imputed to its own CDF phi. We have x, y, z being normally distributed, standardized, and i.i.d. Let's start by the first question here. So what is the expectation for the following expression? We have, and this is z being imputed to its own CDF, so this is actually by the universality of the uniform, just a uniform. However, we're going to just write it down as is, and we're using lotus here, meaning that we can use this expression as it is and use the PDF of z without having to find the PDF of this whole expression here. Okay, so we have z squared, and we have the CDF of z, and now it's a little z, and we have the PDF of z integrated over z, and the space we're integrating over is the full support of z. Okay, so the next question is we were asked to find the probability of this event being less than 2/3. All right, so what does that mean? Well, remember that I just told you that the when you insert the random variable to its own CDF, you can use the universality of the uniform, which says that this random variable, when you transform it, it becomes a uniform. It's following, and this uniform is distributed 0, 1 support here, okay? And that is, now we're in the domain of the uniform, and that is just the length of the uniform, the probability of this event being equal to the length of it. So what does that mean? Well, basically what it means is that if we have the PDF of the uniform going from 0 to 1, it just means that we are in this space here. This is saying we want the 2/3 is just here, and we want the probability of this space divided by this whole space over here, right? So, and that is 2/3. Now, there's another way to think about this problem. I mean, this is the simplest one, but say that you didn't really see that you could use the universality of the uniform. This would lead us to a slightly more complicated function, but I believe it's really nice to go through this calculation to see that it also adds up. So let me say this is method 1. Method 1, we just use the universality of the uniform. Then method 2 would not use that, but go on to use properties of the the standard normal to find that this expression here amounts to 2/3. All right, so let's do that. I'm going to copy this here, and so right, so how would we proceed here? Well, we're trying to get this random variable cleaned up so it's only z in the left hand side of the inequality. So we could take the inverse of the CDF. Right, now we have this whole expression being expressed in the z variable. So, and this to the right hand side is a constant. And so what is this constant? I mean, the fun part is that in R you can check what this is, and it turns out to be something like 0.4307, and in R I'm going to post some code for you. We can check it out together. And this, if you put this into the Q norm function in R, you will see that this, and then that number into the P norm to get the distribution, the probability of that event in the standard normal distribution, it will become 2/3. Now, let's think a little bit more about what that means. And I would draw the following graph here. So let's see. This is the CDF of Z. It goes something like this. This is not exactly right, and this goes from 0 to 1. This is on the probability scale, and we're going to plus infinity on this side, minus infinity on that side, and imagine this is one standard deviation to the plus side. This is something like the standard deviation to the minus side. And what we are doing by calculating this expression here, when we put the 0.4307, we are essentially asking what is the probability of this event here. That will give you the 2/3. So the 2/3 basically means that we are putting this number here into the CDF of the normal, yielding the 2/3 number. Okay. All right. So the last question here is now about finding the probability of this event, which looks fairly complicated. And if we're going to tackle this, I mean, the most normal thing would be to use the CDF of the joint distribution of x, y, z. So what would that mean in an integral expression? Well, it would mean that we were integrating over the space of x, y, z, and this is then, I'm going to write this as an indicator variable, meaning that we're only considering, and these are now small x's, only considering events where this is true, this event is true. All other places will be z set to 0, and we're then multiplying by the joint distribution of x, y, z over this it will be an area. Well, it will be a cube here because we're in a three-dimensional space. And I mean, this looks really tedious. So another way to think about this problem is to ask, what does it mean that this event is true? And this will lead us to the following little trick. So as x, y, and z are i.i.d, so they are independent and they have the same distribution, and this trick will not apply immediately if i.i.d doesn't hold. And so we can think about, and this will lead us back to the classical or the naive definition of probability. So we think about positions here, and well, let me just define what the classical or the naive definition of probability means. Well, it means that of a probability of an event, let's call it B, event B, just means that we're taking the number of favorable events, divided by the number of possible events. Right, that's what we did in the beginning of Stat 110. And what are the number of favorable events? Well, the favorable events that we are interested in is the events where x, y, z has this order. So that's just one. The number of possible events, well, x could go anywhere here, right? To any of these positions. And so x has 3 options to begin with. And then y can take any of the remaining positions. And so if x took this position, y could only take these positions here. So it will always be 2. And z will take the remainder of positions here. So let's just call it y. So now we see that this is just a 1, 3 factorial. And that is 1/6.